So you're in for a special treat today because we're going to start to look at the idea of so-called counter space or negative space or co-space. It's a very real geometric idea which is rarely discussed, and some of the people who are really into it believe that actually a lot of physical principles or maybe principles of biology could be discovered by studying this so-called negative space. So what is it? Well, basically, it's just involving using the idea of duality. I've done something called a polarity here. So this line is like the kind of mate or twin with this point. And if I take the point outside of a circle, the line goes inside. In this special case, you can see that actually this line, this dual of this point, is actually just the place where the tangents meet the circle. It's joining where the tangents meet the circle. But later I'll give you a more general definition of what these kind of polarities are. The real point, though, is that this is a system by which, basically using the conic, the circle in this case, as a sort of portal, one can travel between this kind of ordinary space, which is point-based, and a kind of line-based space. And there are also some connections to do with things like circle inversion. Now, the main thing I wanted to do today was just to show you some quite nice examples of these things actually working. You know, negative space, rather than thinking about objects being made out of points, you're thinking about objects being made out of lines. So here you see this ampersand curve, or kind of like a warped figure eight. And we're thinking of that as a set of points for now. And you can see it's partially contained within a circle. Now what I'm doing, I'm moving this point around the ampersand, and as I do so, I'm keeping track of all of the lines which are generated. So I'm sort of leaving a trail of all of the duals of the positions where the point was. And you can see how this is forming a kind of enveloping shape or something. And what's really interesting is to compare it with the shape of the initial thing inside the circle, because you'll find that there can be many kind of opposites. Something which was inside the circle before will be outside the circle afterwards, and so on and so forth. So I shall just leave it to you to have a look at these nice examples. Okay, so I thought it was really fascinating to see how the different parts of the curve in the ordinary space inside the circle are reflected by configurations outside. And since I find it easier to work with point curves, I was trying to think of a way to convert this outer structure, which is really assembled out of lines, to some kind of pointwise structure. And so what I ended up doing was I had a pair of points travelling around this figure eight track, which are very close to each other, and both of those generated a dual, a line, and then I found out where those two lines intersected. And so essentially that gave a sort of point-like representation of some of these shapes. Now, this works quite well in certain cases, but it's quite computationally challenging for the computer to do, because it involves laying down a lot of points, and the thing's often going to infinity and such, because, for example, the dual of a point in the middle of a circle is the line at infinity. So the computer has to work very hard. And I started to fiddle around with it and look at what happens if these 2 points are going at different speeds. And this happens to be a really nice ingredient for getting some quite fun fractal dynamics and things that look like chaotic attractors. So I shall just leave it with you to see the rest of these videos and then wind up by explaining how these polarities are actually performed. And it's actually remarkably easy to create these things in GeoGebra. And it's a good way to explore this co-space, which, in all honesty, is just as genuine a thing and just as valid a thing as the ordinary space of points which we do Euclidean geometry on. It's just thinking about a space of lines is somehow less intuitive to us. But this is going to come in very useful when we step up to the three-dimensional case. And in that case, there's a certain school which believe that the kind of aspects of this negative space have a lot of relationships with various things in nature, such as the sun, how the plants grow, how gravity works, and so forth. So I encourage you to explore this kind of idea, technically known as a polarity or a projective correlation. I mean, there are many different ways you can sort of get from ordinary space a negative space. Perhaps using the circle or a conic and doing this kind of polarity idea is maybe the simplest. Okay then, so all of these ideas about using the circle to sort of access this negative space all revolve around the idea of being able to work out the duals of points and the duals of lines. Now, I'll show you how to work out the dual of a point. In this case, it'll be inside the circle, but this method works anyway. So it's interesting how the method works because it involves quite a lot of choice. You start off by just drawing any two distinct lines through this circle. Each line has to meet the circle at 2 points. And so then there are 4 points around the outside of the circle where you've just intersected with lines. So if you mark those 4 points, they obviously form a quadrangle. And now if you complete that quadrangle by drawing the other lines between those 4 points, you can find these other places where these edges intersect. So a couple of edges intersect in that point in the middle that we have, but they also intersect at the left, and they also intersect somewhere near the bottom right, bottom left. These are in fact called the diagonal points of a complete quadrangle. Now, the point here is that we can use this information to determine the dual of our point. How do we do it? Well, it's very simple. We just connect together the two diagonal points, which are not equal to the point we're interested in. That'll give us a line, and it happens that that line is in fact the polar, the dual, of the initial line. So it's quite remarkable really that such a simplistic procedure, just involving using straight lines, no compass or anything, once you've got your circle, you can work out the dual of these different things just by doing straight line constructions. So that's how you can find the dual of a point, and it works whether you're inside or outside of a circle. Also, GeoGebra just has a command which does it automatically. And then you also should know how to convert a line into its dual, which will be a point. Okay then, so one problem is to... Okay, so another important problem then is to be able to work out what the dual is of a line. So if you have a given line, if you can find a couple of points on that line, any will do, but preferably outside of the conic, and so you can choose those, and then by the previous method you can work out what the dual of those points are. So the dual of this yellow point is this yellow line, and the dual of a red point is the red line. And where they meet is in fact the dual of the original blue line. This is really to do with the central fact